Hello everyone, welcome to this module on risk-based site investigation strategy. In geotechnical and environmental engineering, site investigation is one of the most critical stages of any project. And why is that? Because every design decision depends on understanding subsurface conditions accurately. And the thing is this, many engineering failures, including foundation collapse, slope instability, excessive settlements, groundwater problems, and even cost overruns can often be tracked back to inadequate site investigation. Now, traditionally, engineers actually used to approach site investigation by just collecting as much data as possible. However, in modern engineering practices, there's a kind of slight difference. There's a recognition that not all risks are equally important. Now, some ground conditions may pose serious threat to safety, maybe cost, schedule, or environmental performance, while others may have minimal impact. Now, this gives rise to the concept of risk-based site investigation. That's what is practiced now compared to the traditional, where investigations are planned strategically to identify, evaluate, and manage the most critical ground-related uncertainties. Now, in this lecture, we'll be examining some things. We'll be examining the difference between traditional and risk-based approaches, the observational method, ground risk registers, value engineering principles, and how these concepts integrate into practical engineering decision making. By the end of this module, I think I should just let me talk slowly. By the end of this module, you should understand how to design smarter, more efficient, and safer site investigation programs. This module is structured around four major concepts. The first concept is risk-based site investigation approach. And here we study how investigation strategies have evolved from routine data gathering into targeted risk management system. I already talked about that. Now the second concept is observational method. Now this method recognizes that subsurface conditions are uncertain. Yeah. And therefore encourages continuous observation and adaptation during construction. Now the third concept is the ground risk register. This is a formal tool used to identify and manage risk associated with ground conditions throughout the project lifecycle. While the fourth concept is value engineering. This focuses on achieving the best balance between costs, safety, quality, and performance. I'll go into details about all of these things in the lecture. Now let us consider the learning outcomes. At the end of this module, you as students should be able to, one, explain the philosophy behind risk-based investigation, be able to now differentiate between the traditional and risk-based investigation approach. I expect you to be able to describe observational method and its application, be able to prepare and interpret a basic ground risk register, apply value engineering concepts to site investigation planning, and integrate all these concepts into practical engineering workflows. These learning outcomes are very important actually because in modern engineering, emphases are usually on optimization and risk management rather than excessive conservatism. Let's see the traditional versus historically. Site investigations followed what we call the traditional approach. In the traditional method, this is what happens. Investigations were largely standardized, meaning that there's a standard. There was a fixed standard. There was a fixed standard for how to do site investigation. So in other words, it was not location based. It was a matter of when we get here, this is what we should do, this is how we should do it. Like, let's say, like a predicted standard. It also involved, that means that boreholes and tests were conducted according to the fixed patterns. The objective usually was to collect large amounts of data. Little emphasis was placed on identifying the most critical uncertainty. And while this approach was useful or produced useful information, it often resulted into sometimes unnecessary testing because it's the standard now. You just have to do it even when it's not even necessary for that location. Increased project costs, delays, and sometimes failure to identify the most dangerous risks. And that's what has led us to this new approach, which is the risk-based approach. Now, it changed the philosophy of the traditional way. Instead of asking what information can we collect, we are now asking as engineers what uncertainties could threaten the project most seriously. That's it. So the approach prioritizes something: critical hazards. It prioritizes areas of greatest uncertainty, potential consequences, probability of failure, and also the sensitivity of the project to ground conditions. I'll give an example. Now, if a project involves a shallow foundation on a competent soil, now extensive deep drilling may not be necessary, right? Yeah. However, if the project involves soft clay, maybe a landslide prone slopes, or a contaminated ground, or even a karstic limestone, then investigation efforts become more intensive. Why? The risks are higher. You see now, so the major advantage of the risk-based approach is that one, it helps to improve safety, it's cost efficient, and resource allocation, improves resource allocation, and also helps, improve decision making. It's therefore a matter of more targeted investigation strategy. So this time we are coming up with strategies that are needed, required in that particular project, not just because this is the standard. So we're going to be looking at the observational method. I already mentioned that earlier. The observational method was promoted by the geotechnical engineer Carl Tegazi and eventually formalized by Ralph B. Peck. So we always usually know it as the Peck philosophy. Peck described this method as learn as you go. Yes, because it's observational. The observational method actually recognizes an important fact. One, subsurface conditions can never be known with complete certainty before construction begins. Therefore, instead of relying only on pre-construction predictions, what do engineers do? They now monitor actual ground behavior during construction. They compare observations with predictions and modify designs if and when necessary. Now, this philosophy has three main principles. One, you predict likely behavior before construction. That's why doing observation doesn't mean that we are cancelling prediction. So predict before construction. Construction, we still observe actual behavior during construction, and then there's an adjustment of design or construction methods when the conditions differ. Now, this method is especially useful in tunneling, deep excavations, embankment constructions, earth dams as well, and projects involving uncertain geology. I'll give an example again. Let's say engineers predicted that settlement during embankment construction will be 50 mm. During monitoring, the actual settlement reaches 90 mm. See, the observational method allows the engineer to respond immediately by doing any of the following: reducing loading rates, or installing drainage, reinforcing foundations, or modifying the design altogether. This method improves safety because decisions are based on real field performance rather than assumptions alone. Now, the observational method can only succeed if four essential requirements are present. Now, this requirement is number one, establishing reliable prediction. Yeah. Engineers must first estimate predicted groundwater behavior. Remember, I already told you that we have to make predictions. That we're saying is observation. That doesn't mean we will not still do our desktop study, take all the normal samples and test them and all that, and make our investigation, the available sites investigation data, laboratory testing, and engineering judgments. Now, like I said, one, establishing a reliable prediction. Two, defining acceptable limits. Before you even go to the field, you tell yourself that, or before the construction, engineer has to define what behavior is acceptable, what level becomes dangerous, because we are predicting that there may be a change from our prediction. So at what point is this, or at what level has it become dangerous that things has to change, and at what threshold where is intervention required. For example, you can be asking what's the maximum settlement we will expect, what maximum pore water pressure, what's the maximum lateral movement that will make us, consider a change. Now, the third requirement is monitoring and observation. The project must include instrumentation and field monitoring, such as settlement plates, piezometers, inclinometers, extensometers. Continuous monitoring provide real-time information about the actual ground performance. And the fourth requirement is a pre-planned correction actions. like we said, there has to be, intervention if things change. So even at that, when you predict there can be change, you should have a pre-planned correction action. So if monitored values exceed acceptable limits, and Nigeria must already know what corrective measures to implement. For example, you may think of maybe ground improvements or additional drainage, structural reinforcement, or construction modification altogether. Without pre-planned actions, you know what happened? Monitoring becomes useless. I mean, what's the use of monitoring if you don't know what to do? That means the engineers will just observe problems without knowing how to respond. So the key idea here is that the observational method combines the following: prediction, that's what you take notes, monitoring, feedback, and then adaptation. Very, very important. So having talked about the observational method, I want us to go and look into the ground risk registers. What's a ground risk register? A ground risk register is a formal document used to identify, remember I said the documents are to identify, to assess, and manage risks associated with ground conditions. It is essentially a structured database now of all identified geotechnical uncertainties and hazards. Yes, geotechnical uncertainties and hazards. Now the purpose of the register is this: it is to ensure that risks are recognized early. Two, responsibilities are assigned, mitigation measures are documented, and risks are continuously reviewed throughout the project life cycle. Now the typical risks recorded include soft ground, differential settlements, high groundwater table, contaminated soil cavities, liquefaction, slope instability, expansive clay, and rock fracturing. Now I just said that all together, but actually it has a category. It's categorized into structural risk, into geotechnical risk, and contamination risk and the rest. Each risk is usually assessed based on one, the probability of occurrence, severity of consequences, overall risk level. I'll show you very soon in the register itself. An example of the register: ground risk registers are important because one, they improve communication. Yes, it improves accountability, decision making, and project transparency. Now, even if maybe another project manager or another engineer takes over a project, with the ground risk register, he can know what is on ground, what is happening, what has been done so far, what has been adapted. For example, if contaminated soil is identified during a preliminary investigation, the register will document the hazard. It will document the potential environmental impact. It will document required testing, also possible remediation methods, and the personnel responsible. Usually, you will have somebody that is assigned to ensure that things are going as in are being that the register one that things are actually registered, identified risks are registered, and identified hazards are registered, and that whatever recommendations are made actually being implemented. You need somebody like that. So let's look at the components of a risk register. The major components of a ground risk register. One, it's a ground risk register typically contains a risk identification number, as you can see, description of hazard, likelihood, consequences, risk rating, pardon me, mitigation measures, responsible party, like I said, whoever is the personnel that is responsible, status of monitoring, because as we are monitoring, they may make adaptations. The status of it also has to be recorded. Now the example table shown now on this slide demonstrates how risks are categorized and managed systematically. Now observe the risk matrix. The matrix combines probability with consequences. Okay, same thing as impact and likelihood. Likelihood and impact for consequences, probability for likelihood. So for example, a low probability but catastrophic event may still receive a high risk rating, meaning that the probability of that thing occurring might be low, but the event is a very high risk one. I mean, it's a catastrophic event if it happens, so it can still receive a high risk rating. But a frequent, maybe something that that can come up every now and then, but it's a minor issue, might actually receive a moderate risk. So for example, suppose soft clay causing foundation settlement has both high likelihood and high consequence. That means it becomes a priority risk requiring immediate mitigation. So you can see how this risk matrix help, how the and why the ground risk register is very, very important. So in such a case now, mitigations mitigation strategies for, like, for a place that has soft clay and already, that can suffer foundation settlement and all that. And this high risk priority now, mitigations could include pile foundations, ground improvements, preloading, or redesign. Now, the risk register is not a static register. It is continuously updated as new investigation data become available, yeah, as construction progresses, and also as site condition changes. So the dynamic nature of the ground risk register makes it a very powerful management tool. You can understand what is going on per time. I hope you get that point. I hope you were able to understand this ground risk register. I hope you understand it and understand the essence of it. So let's look at value engineering when it comes to site investigation. Now, value engineering, what does it do? It focuses on achieving the best engineering outcome. Usually, you're considering at the lowest total cost without compromising safety or functionality. Please take note of that. It does not mean cutting costs. No. Actually, in site investigation, a value engineer will ask, are we spending investigation resources where they matter most? We are looking at how to optimize, the resources available to get the best engineering outcome. Yes, low cost, and yet without compromising safety. If you're compromising safety and functionality, then that means already you're not talking about value engineering anymore. I'm sure you guys must have remembered when Prof was saying a lot of money goes to doing a very good engineering job, and that's why some people cut corners. Yes, so it's in this value engineering now that you try to, like, evaluate, okay, what is the minimum we can spend to get the best, right? Even though you're being trained as engineering geologist and environmental geologist, the truth is that you have to understand economics. You still have to understand costs, implications of strategies that you'll be recommending, or if you had to go for site investigation, you handle a contract, you should be able to still know how cost comes in. So the thing is this, like I said, it's not cutting corners. Instead, it means optimizing investigations intelligently. For example, let me give an example. Instead of drilling many unnecessary boreholes in low risk areas, resources may be concentrated in critical foundation zones, areas with uncertain geology, or environmentally sensitive region. I do also remember that Prof gave an example where he said that okay, in our last meeting where we had this example of a very bad road, and he said, okay, that the engineer decided to locate the place with the worst geology, and decided to do a very good job there because they couldn't have put that kind of reinforcement in all of the road. So they chose the place that had the worst geologies, that had the most problematic areas. So these are some of the things that you can in engineering in value engineering that you put to consideration. Also look at environmentally sensitive regions. So value engineering actually considers costs, it considers risk reduction, it considers the project performance, construction visibility, and long-term maintenance. Now, a proper value engineering process will usually involve the following: one, identifying project functions; two, evaluating alternatives; three, comparing costs and benefits; and four, selecting the most efficient solution. So for example, two foundation solution may both work technically, a deep pile foundation or shallow foundations with ground improvements. So a value engineer evaluates which option provides the best overall value, considering the cost of construction, the time, the risk, durability, and future maintenance. I seem to be repeating myself, but just so that it can sink in. So, value engineering supports smarter engineering decisions, not cutting corners. Now, let's integrate everything that we have been talking about. I've said a lot of things, and so this class slide now showing that all the concepts we have discussed, work together and how it works together in practical engineering projects. The workflow usually begins with one thing: preliminary site investigation. That's initial geological and geotechnical information is collected. After that, you have your risk identification. You want to identify the potential hazards, the uncertainties, will also be identified. After then, you now do an assessment of those risks. Now, the significance of each risk is evaluated. After this, you now do what? Investigation planning. That's where you allocate resources strategically based on identified risk during construction. Don't no during what's the word? Resources are allocated strategically based on identified risk. However, during construction, you will now have your observational monitoring. After all these things, so the next thing is observational monitoring. Why? You want to check the actual ground behavior. You have to continuously monitor it. If observation differ from prediction, then you get to the next stage, which is adaptive management. So corrective actions are implemented throughout the process. Excuse me. So it's corrected throughout the process, and then remember, our ground risk register has to be continuously updated. You're writing down what has been identified, the mitigation measures that are suggested, and the current situation or status of the project. And then, of course, value engineering, which we just finished talking about, to ensure cost-effective optimization. Now, to integrate the integrated framework, improves safety. When we put all these things together while investigating a site, one, it improves safety, efficiency, sustainability, and project success. So modern geotechnical engineering increasingly relies on this integrated approach, because why? Ground uncertainty can never be eliminated completely. The truth is that it can only be managed intelligently. And so before I do the summary and key takeaways from this module, I want to quickly give a mini case study. If in a mini case study, for example, of a proposed high-rising building, on a reclaimed coastal land. So this is the case study. They want to build a high-rise building on a reclaimed coastal land. Now, let's evaluate what are the potential risks. One is going to be soft compressible soils. Yes, in most reclaimed lands in the coastal region, that's one problem you can encounter. High groundwater, right? Differential settlements. So these are potential risks you can predict. Then you now go into the investigation strategy, which will include CPTU, boreholes, geophysics, and groundwater monitoring. When you now actually monitor the groundwater, you can be sure of the exact level where the groundwater table is. You can get the exact levels. You can from the geophysics, you can tell a lot many things happening in the subsurface. And then we have the observational method. Yes, the observation method can support the stage foundation design. Yes, as you're doing it, after doing all these things, you now begin to have your observational. I want to believe that you already I didn't have that in my slide, but I just thought about it and said, let me give like an example. Someone want to have a project, you check the risk, you tell yourself what strategies am I going to use. The what strategy do you use investigating, the field, and then of course the observation and while the foundation is being done. So let's talk about the summaries, right? Good. So let me give you a recap and key takeaways from this particular module. In summary, this module introduces the philosophy and principles of risk-based site investigation. Now, we learned that traditional approaches often focus on excessive data collections, and that risk-based approaches prioritize critical uncertainties and hazards. We also studied the observational method, which relies on prediction, monitoring, feedback, and adaptation. We discussed ground risk registers. Sorry, we discussed ground risk registers as structured tools for identifying and managing geotechnical risk. Now, we also examined value engineering as a strategy for balancing safety, cost, performance, and efficiency. Finally, we saw that I will show how these concepts integrate into a modern engineering workflow. So the major lesson from this module is that successful site investigation is not simply about collecting data. It's about one, understanding uncertainty, managing risk, making informed decisions, and adapting intelligently to field conditions. So I want to believe that you already get the recap, the bottom line of this. Then I'm going to be giving you an homework, or is it an assignment? Well, homework assignment. Ideally, it's something we're still going to discuss, when we meet for our discussion class. And that is, I'll just, read it out. Or I'll just say it. We're thinking of designing a preliminary investigation strategy for a bridge crossing a river valley. Now, there's a bridge that's going to be crossing a river valley. So what I want you to do is to design a preliminary investigation strategy. Yes, what's the preliminary investigation strategy? To identify key geotechnical and hydrogeological risk, prepare a simple ground risk register, and explain how the observational method could be applied during construction. I'll take it again. I'm going to repeat it, even though I know you can always move the video back to, pick it. So that I'll say it again. Design a preliminary investigation strategy for a bridge crossing a river valley. Identify key geotechnical and hydrological risks. Prepare a simplified ground risk register. Explain how the observational method could be applied during construction. And that's it. So do have a nice day and see you in the next class. And that's the advanced ground modeling, right? Cheers.